Hello and welcome to my talk about customizing and refactoring Gradle builds. I'm Marc Phillipp. This talk is going to be in English because we wanted to have more English talks at this conference. But I'm German. I actually live in Karlsruhe, so if you have a question, of course, feel free to ask it in German as well, or in Badisch, Alemannisch, Schwäbisch, whatever you want. We can translate that. All right. So just a little bit about me. I work as a software engineer at Gradle. Gradle Inc. is the company behind Gradle. I'm also the JUnit team lead, so you might have seen some other talk by me previously. So most of my talks have been about JUnit so far. All right. At first, I want to talk a little bit about what Gradle really is, because it's a little bit confusing, because there's Gradle, the build tool, there's Gradle, the company. There's a thing called Gradle Enterprise, just to clarify what these things are. So first and foremost, Gradle is an open source build automation tool. It's based on a Java virtual machine. It's implemented in Java, so it kind of need Java to run it. But it's not really just for Java, as we will see in a moment. Its focus is flexibility and performance, and the basic concepts are applicable to whatever language you're working with, basically. It's 100% open source and free, so it's Apache licensed, and it's backed by a commercial company, yes, but the tool itself is free and open source. Yeah, it's versatile, so you can use it for any Java ecosystem language, like Java, Groovy, Kotlin, Scala, and so forth. It's also the official build tool for Android, so if you ever worked on an Android app, you've probably come across it. But you can also use it for native projects. So if you have a C or C++ project or a Swift project, you can also use Gradle. And there's other ecosystem tools like ASCII Doctor, for example, which has a really good Gradle plugin and helps you build documentation along with your source code at the same time, the same build. A few words about Gradle Inc. Our vision is build happiness. So that means we want you to be happy with the build, but also we want to help, that the build is not something you dread working with, but something that actually is enjoyable to work with. It's fast and reliable and really helps you to accelerate your developer productivity. So this is really important. Of course, you would rather spend your time working on production code than on the build, but sometimes you do need to work on the build, and there will be build failures that you need to figure out what's going wrong. And then in that case, we really want to give you the tools as a company to find out what's going wrong, why is the build slow, and so forth. And this is where Gradle Enterprise, which is our commercial offering, comes into play and is kind of something that helps you with Gradle and Maven builds to visualize how our build times developing over time. What are the most common failures? Why is this build so slow? Which task or which goal is slow? And those kind of questions you will often have. And this is where Gradle Enterprise really can help. All right. The agenda for today is I want to go over some basic concepts that are really important to understand what Gradle does. And then we're really going to dive into the conference motto, quick and dirty. And I'm going to show you some things that you can do with Gradle, and it's okay. It's a quick and dirty way to do so to some extent, but at some point you should really refactor those. And I will give you some examples how you can do that today. So I named this from quick and dirty to safe and sound. And I have 3 areas prepared for today. One is dependency management. So what shouldn't you do there? What should you do there? How should you do this with Gradle? Custom tasks. So sometimes you want to just add a task to your build that does fulfill some special requirement, and we'll see how to do that. But also then how to refactor this task into something that it can be tested independently from your build, and so on. And the same holds true for custom configuration things, like you want to have another source set for integration tests, for example, and you want to configure that. And Gradle allows you to do that, but you really want to separate different concerns, and Gradle provides you with the tools to do so. And we will see that in the remainder of the talk. Before we really start, I want to know how deep I should get into those basic concepts. So let's do a quick show of hands. I would like to know of you folks, I should say, who here has used Gradle before? Okay, almost everyone. Who's used it on a production project? About the same amount. Who's using it every day? Okay, only a few. So I think we should go over those basic concepts. And I'll try to make it quick so we can really get to the hands-on coding as fast as possible. So one of the basic concepts in Gradle is a task. So a Gradle build, when you try to think about, okay, I want to run my build, you always think about, okay, which task do I want to run? What do I want to do? And this is like the core unit in a Gradle build. A task can then depend on other tasks that would also get executed if you target this one task. And really importantly, a task can have inputs and outputs. So for example, think about a Java compile task. The inputs are pretty clear. It's the Java files, all the compiler flags, basically whatever influences the output of the task, which are the class files in this case. And the same concept applies to all the tasks that are there in Gradle. So this would be a hello world example in Gradle. Of course, you wouldn't really do that in your build. So just a quick thing to do is I can register a hello world task. This is what the build script here does. And then I can just register an action that would be run last when the task actually is executed. And in this case, it just prints hello world. So and if you run that, you can see that below here. You run the task hello world. You tell Gradle here to run it. And then the output will be shown here. So this is like hello world in Gradle. We will see more useful tasks later. Another really important thing to understand are build scripts. A Gradle project is configured in build scripts. So there's two kinds. There's a settings.gradle, optionally .kts script, which contains the root project name, for example, or it lists like all the subprojects that you want to include in your build are listed there. The second script is the build.gradle file. There you configure the used plugins. So Gradle also has a plugin concept, and you can add tasks like the hello world tasks we've just seen, or you can configure tasks, give them different settings, that kind of thing. That goes to the build scripts. So here's an example of a settings script, which is just like assigning a name to the root project and including two subprojects. So those are usually pretty simple. A build script is usually a little longer. So the first thing you do in the build script is you select which plugins you want to apply. So in this case, we're going to apply the Java plugin because this is a Java project and we want to compile Java sources. We're also going to apply the application plugin because in this case, we have a main class and the application plugin can generate some startup scripts for us so we can run this class on Unix systems or on Windows without figuring out all the Java parameters that we need to set. That's the first part. And in this case, we also have some dependencies. For example, we depend on Guava here and on JUnit. So we can list those here. And you already notice, okay, we have implementation and test implementation here. So that's like similar to a scope in Maven. Basically, we say, okay, Guava I need for my implementation, and JUnit I only need for my test implementation. And where do these dependencies get resolved from? Well, that's what the repositories block here is used. So in this case, we're just going to use JCenter. This could also be Maven Central or some custom repository. That's basically up to you. And then the last block in here is the application extension, which comes from the application plugin. So a plugin can register extensions. It can register tasks. An extension is usually used to configure the plugin. In this case, the configuration is really simple. We're just saying, okay, the app class is our main class here, and please use that when you generate the startup scripts. So this is kind of really declarative. You just assign a few values, basically. You list your dependencies. There's no real logic in these build scripts. You can, however, use Groovy or Kotlin to do them. So they are either written in Groovy DSL or in the Kotlin DSL. So when Gradle started initially, Kotlin didn't even exist. So Groovy was the really only language at the time that allowed to build these kinds of DSLs in code. So Gradle was started with Groovy. And Groovy is a fine language. I really like Groovy. It just has a disadvantage. It's dynamically typed. So building IDE support, like code completion and these things, is kind of hard to do with Groovy in general. And that also has effects on the Groovy DSL being not the best for editing and things like that. So once it works, but yeah, getting there sometimes is hard. Which is why as soon as Kotlin became popular, the Gradle team started working on the Kotlin DSL. And Kotlin is statically typed and supported by JetBrains. So at least in IntelliJ IDEA, you get a really, really good editor experience already. And there's still work going on to make it even better. So I'm going to get there. These two DSLs are available, and you can use them. You can choose which one you want. You can use both in one project if you must, or if you want to migrate step by step, you can do that. And Gradle will support both indefinitely, so it's not like one is deprecated and everyone has to use Kotlin DSL now. That's not the case. But yeah, please remember here, build scripts should be declarative. So even though you have the full power of a programming language at your hands, you should use it with care. Yeah, because then you can create a mess of procedural code in your build script, but you shouldn't. All right. Another important piece to understand a typical Gradle project is the Gradle wrapper. The Gradle wrapper is basically a shell script that lives in your project. It's committed to source control. There's one for Windows, there's one for Unix. And instead of calling Gradle directly, which you would have to download before and put in some directory and add it to your path, you can call the wrapper script, and it will look at its configuration and download the correct version of Gradle for your project for you, or it will only do that, of course, if it's not cached already locally. So it only will download it once. And this way, all machines, every developer, the CI server, everyone will use the same Gradle version. And that's a really useful thing, and which is why most Gradle projects use the Gradle wrapper. Okay, now we're ready to look at the structure of a typical Gradle project. I used the Gradle init task in this case to generate one for us. We have a build script then in the root folder, and also a settings script. And then we have a few files that belong to the wrapper. So there are the two scripts, one for Windows, one for Unix, and the configuration file in a small jar that handles the downloading of the distribution for us is also included in there. And then all the rest is your files that belong to your project. For example, in a Java project, you would have a source main Java folder, and the Java files would be in there, and so forth. Now, another really important concept about Gradle is incremental builds. We want the builds to be fast and reliable, and incremental builds is kind of hard to get right. So an incremental build means we don't call clean on every build, right? You want to reuse the outputs of the previous build and only redo those things that you need to do again because things have changed. And Gradle really excels at this because it tracks the inputs and outputs of each task and also the task implementation. So if you run one build and you make some changes to your code, for example, and you run the build again, Gradle will check for every task that you asked it to execute, have the inputs changed. So for example, it will analyze all Java files, it will compute a checksum for them, and it will check, okay, has any of these files changed? Are the files all still present? Or maybe someone has deleted a class, and I also need to delete it from the outputs, that sort of thing. And it will also check that the outputs that have previously been produced are still present and unchanged. So whatever's in the build directory, that's the usual place the outputs get put. If anyone has made any changes to that, the task will get executed again. And last but not least, the task implementation is tracked. So for example, if you upgrade a plugin or if you use a different version of Gradle, then the task implementation has changed and it could be doing something different the second time it is executed. So therefore, it's also tracked. But if none of these three criteria are fulfilled, the outputs of the task are kept and the task is considered up to date and will not have to be executed again. A short example here for a small project, I just call the build task here. And the first time all 7 tasks are executed, If I do this again, in this case without any changes, Gradle will see, okay, none of the inputs, outputs have changed. The task implementation is the same. So all the 7 tasks are now up to date. And it didn't have to do anything, really. Yeah. So this is one of the really crucial things to understand. Whenever you type clean in Gradle, you're probably doing something wrong. All right, next is build scans. Whenever you have a problem with your build, you need some way to analyze what's actually going on. You actually want to have something that you can show someone to look into the problem with you, maybe, or just like have a record of the problem, what actually happened during the build. And a build scan is exactly that. So if you run Gradle with ---- scan, you will get a build scan at the end. So basically it's a URL that's printed at the end of the build, which you can open. Yeah, it's on scansgradle.com. I'm not sure you can see that. So it's a public service that Gradle provides. It's free to use. You can basically, you get a summary of what happened during your build. You could look at the console log, and you can always link to one of these lines and send the link and share that. You get a timeline, so you can see all the tasks that have been executed. You can even take a look at why the task was executed. So for example, the compile Java task in this example says, okay, the app Java file was changed. That's why I executed it. So you can like really reason what happened during the build. You get performance insights. For example, you could look at, okay, the garbage collection time. Is there anything worrying here? Maybe I need to give my build more heap space or something like that. You get a record of all tests that were executed. In this case, it's only one. It's not very interesting. It's only a single module built, so there are no projects. You can look at all the dependencies that have been resolved. And you can also go down and see from where they were resolved, which repository was used to resolve this dependency. And it provides a lot of insights into your build in case something goes wrong. Yes, so this is free to use on scansgradle.com. The data is somewhat public, of course. The link, I mean, is not really easy to guess. So it's a private link in that case. If you don't give it to anyone, no one will ever see it. But the data is out there. And of course, before publishing it, you have to agree to some terms of service and that sort of thing. I kind of did not include that in the example here. Gradle Enterprise also has that, so you can have that on your own server, for example, if you are interested in that. Last but not least, the build cache is an open source part in Gradle. And similar to incremental builds, it allows reusing the outputs of a previous build. But in this case, it's not just the previous build, but it could be any previous build. So if you have run a build last week, and now you're switching to that branch again, and you're executing the same build basically, then it can reuse the outputs from last week. It will see that all the inputs are the same, and you can just not execute it, instead get the outputs from the cache. And there's a really easy way to enable it. Basically, you tell Gradle ---- build cache, and you will already get a local build cache that is only on your local machine. And you will store artifacts in there and can get artifacts out of there for the next build. There's also the possibility to have a remote cache that is also checked in case the local cache doesn't have the entry. That's also possible. And we provide a free Docker image, a free jar file. So if you want, you can use that free of charge. It's not commercial in that sense. If you have Gradle Enterprise, it's also included there, of course. But you can also use that just without any paying anything for it. And the local and remote cache kind of have a good interaction model. So if you don't find something in the local cache, you will check the build cache will automatically check in the remote cache and then store it in the local cache for the next time around and that sort of thing. And yeah, I encourage you to try it locally. It's just a local cache. It doesn't cost anything. You don't have to set up anything. It's just a really nice thing, even for your own experience. If you work on a project, be it an open source project, for example, it just makes things faster, and it's really nice to work with. All right. Now let's get to the more practical tile of the talk. Tile? Oh, that's German. I meant part. Sorry for that. At least I noticed, so that's that's a good thing. So the practical part of the talk, I meant to say. And first, we're going to kind of make a mess with dependency management, and we're going to clean it up again. So I'm going to do this in a demo. So I have a little project set up here. It is just a 2 sub-project build. So there's a CLI project and a lib project, and the root project is called Gradle Refactorings. The other projects are here. There's no root build script in here, but the sub-projects do have one. So for example, the lib one has this build script. It's a Java library, so it applies the Java library plugin. It uses JCenter for a few dependencies, as well as for J, Guava, and JNet. It configures the test tasks to use the JNet platform. That's what this part does. And the CLI one is pretty similar. And we apply different plugins. So because this is not a Java library, it's a Java application, we only apply the Java plugin. And in addition, the application plugin. We also have a few dependencies. And for example, this is a project dependency. So we depend on the other sub-project. If you're wondering what the colon means, basically that's like an absolute path. So this could be nested. The application plugin, I've already mentioned that on the slide. This is the same example, basically, has the app class, which is the main class. Doesn't do much, just prints some strings and calls the library method, which is in the library project. So it's a really simple project, trying to demonstrate some build script things in there. So the code is really, really simple. All right, so we've seen here we have dependencies, and we have used implementation here and test implementation there, which is what we had on the slide. If you look at the other project, it's slightly different. It uses compile and test compile. Does anyone know what the difference is? Is on the runtime class, but in both cases. Let me show you. I'll just give you a simple example. So let's just change this maybe to implementation here. Maybe I should show the build before that. That would be nice. So let's just run this, create a build. All right. So the build is green, right? It's build successful. When I change this now, let's change this to implementation. And this to test implementation. What happens then? I get a compile error. Why is that? So where is the compile error located? It's in the CLI subproject, and it's in the app class. So if I import the changes in here, I also get the compile error in IntelliJ. Yes, you cannot resolve immutable set, which is the class from Guava, and that's because we changed compile to implementation in the lib. So basically, implementation means we want to use this, we want to have this on the compile class path and also on the runtime class path, but we don't want to leak this dependency to upstream projects, basically, or to downstream projects, I should say. So to projects that depend on this project, as the CLI project does, right? It has a project dependency on lib, and therefore it would get all the things that are on lib's compile class path. But usually we want to avoid leaking dependencies, because if you want to really use Guava in this sub-project, in the CLI one, we should declare it in there. So that's why implementation should be really preferred over compile. If you really want this, you can, of course, have it. So you can make this explicit and saying, okay, this is an API dependency. Looking at the class, though, it's not really. So if I had immutable set in here on the public method, right, then it kind of would be an API dependency, because whoever uses this class, which is a public class in this library, would have to have Guava on their class path as well. So if I run this build again, it will be successful this time around, yeah. So that's the difference between API and implementation. So the API thing is only available if you use the Java library plugin, because only then you kind of have an API. If it's not a library, if it's an application, basically everything is implementation, because you shouldn't have any dependency on an application. That would be kind of strange. So that's why API and implementation are two different things. All right. So let's see, what else do we have in here? Well, for example, we have the CLI project, which has an SLF4J API dependency and dependency on SLF4J simple, luckily with the same version. And the same in the library, has also an dependency on SLF4J API and also using the same version. But imagine someone wants to upgrade things, they might forget to adjust the one place, right? So we shouldn't really have these versions in multiple places. We should really have one central place that defines the version. And I'm going to show you a simple way to do that today. So we can have, for example, a simple variable in here. Let's call it SLF4J and just give it that value. Right, and then we can just use that here. That would work. And we can reuse it here. And that would be the same version then, right? Okay, fair enough, but that doesn't really help the other project, does it? So really we want to share this variable somehow and use it in the other project as well. So it's actually a constant, not a variable. So that's what we want. And one way to do that is we can move it to some other object. Let's call it deps. So this is Kotlin after all. We can type Kotlin in here. Let's make a quick and dirty object. And then we can do deps here and deps there. So this still works. But how to get it to the other project? Well, Gradle has a way to do that. So while we currently only have these two projects, we can create a new project that's kind of present by convention. And that's the build source project. So the build source project can take all the code that we need in our build scripts. We can collect it in a central place. We can write tests for it, and so on. And for that, basically, I'm just going to have to create a build script in here. And when I tell IntelliJ to import this again, it will also have some editor support for that. And what we want to use in here is we want to use the Kotlin DSL plugin, because we're going to use the same DSL in our build source project that we can use in all the build scripts. So there's no gap or anything. And for that to work, since Kotlin will resolve other dependencies, we also need to define a repository in here. So, and then we can also create a source folder, source main Kotlin. This could also be Java or Groovy or something. It doesn't really have to be Kotlin. And since I'm using the Kotlin DSL in this example, it would be nice if it were also Kotlin. So that this import is once more, and now it's also a proper source folder because it's blue, right? And we can go to the CLI project, and we can actually move that class to build source. Yes, I know what I'm doing. And now the class is in here, right? And then the build source project, and we can use it in CLI. That's actually wrong. Okay. The import was not necessary. Okay, now it works in the CLI project, and we can do the same thing also in the lib project. Now we can use the deps class because it's in build source, it's available in all the sub-projects. And we can do the same for Guava and for JUnit. I'm just gonna not do it here because it's repetitive work. I think you get the idea. And this way you can use all the editor support that you have in IDEA to work with this class and refactor it and test it. All right, so that's one way to collect dependency versions in build source, just having these constants in here, and you can use them in your build script. It's still a little bit inconvenient because you have to like type this all the time, but at least you get some auto-completion support. Like if you have different versions here, you would be able to select the right one. You could also extract the whole string into some class. So basically, this is really a flexible approach. One other new thing I wanted to show you today is creating a platform that you kind of compile against. It's similar to like a BOM file in Maven. So when I create platform subproject, I have to add it to the settings XML. Oh, no, the settings Gradle script, of course. So I assume if you're paying attention, that's great. A build script. Let's import that. Okay. So the platform subproject, the idea is that we only collect dependency constraints in there that we want to use in our other projects. And for that, there's another Gradle plugin we want to use. It's called the Java Platform plugin. And you can then define dependency constraints to be precise. It's an S missing. So if we go here, and we basically copy these and go back to the platform project, put them in here, replace this with API. We have extracted those out over there, and we can do the same for the lib project. We do have as left4j, we already have JUnit, so let's do this with Guava. So these are just constraints. Right now, no one is using them. What do we need to do to use them? Well, we need to go to the other project, and we need to add a dependency on the platform. It's this kind of special dependency. This is why this platform method is used. And I'm just going to reference the other project, which is called platform. And once I've done that, I can basically go here and remove that again. So I don't need the version here. I can just remove that. And the same for JUnit. And for the lib project as well. Here I can even use the API thing. So it's applied to all dependencies, not just implementation. I can remove the versions. And I can run a build. And it's green. So that means I have a subproject in here that is just responsible for providing the platform that we want to compile against in our other subprojects. So I can collect all the dependency constraints I have in here. I could do more advanced things like align dependencies and that sort of thing. But these are like just the basics. So this is kind of like a BOM, kind of like dependency management in Maven. Okay, let's do a short recap. We've seen that there's an API and an implementation configuration that you should prefer over compile because it makes it more explicit. It doesn't leak dependencies by default. Duplicating dependency versions. I know we all do that sometimes. We copy and paste something just to make it work, and then we forget about it. We shouldn't do that. We shouldn't duplicate this information. We should collect it in a common place. And using build source for that is one approach that works really well. Another approach is a Java Platform plugin subproject that you can use in the other projects to define your dependency constraints. If you're interested more on dependency management, there's 2 blog posts by my colleagues, and there's also a webinar in those blog posts. So they really go into all the details, what you can do with Gradle's dependency management engine. And there's lots of stuff. I haven't even touched the surface of it. Not really. All right. What also will happen from time to time are custom tasks. So let's also see an example of that. Stash that. Check that out. Okay. Good. What have I done here? In my CLI build script, I have this beauty here. I have created a jar checksum task, and what it does, well, it's supposed to compute the checksum for the jar I'm creating, which is why it depends on the jar task. The archive file it looks at is basically derived from the jar task. So we get the archive file from the jar task. This is kind of a lazy kind of API, so I don't actually need to realize the jar task until I really need it. I don't need to configure it. So please just ignore that for now. The checksum file is basically then also the file that the checksum should be written to, is also derived from the archive file. So basically I take the archive file and then just append .sha512. And the implementation basically is in this do first block. So I just basically the callback I give at configuration time to the task that should be executed when the task is when the task is executing. So what it does is it just uses Guava's hashing class. How does it do that? Well, there is a way you can add dependencies to your build script. So what I did here is I added Guava to the class path of my build script, and then I can use it in all the build scripts. So that's possible. And I use this SHA-512 hashing function to hash it, and then I just write the text to the file. So let's execute that. And what it does, in the libs folder, there's the jar file now. It's a bit small. And there's a SHA-512 file, which is basically the checksum file. And this was written by our task. If I run this again, you will see that it's executed again. So I can run this again and again, and it will always be executed. It will never be up to date. And that's one of the things you often don't realize when you do these quick and dirty task implementations inside your build script. It's not actually working properly. So it does produce the checksum file, but it does so every time, even if the jar file doesn't even change. So we don't have to do that. The way to make it work is to actually declare the inputs and outputs of this task. Right now, Gradle doesn't have the slightest idea what this task does. It doesn't really understand the code. Only we do. So we need to help it a bit. So we need to declare the inputs. And one way to do this is to use the DSL for that. So we can say inputs file. So the archive file is the input. And the checksum file is the output. Now, if we run this again, it will execute one additional time. But if I now do it again, it will be up to date. Because now Gradle knows, okay, the input hasn't changed. The output still there. Nothing has changed. The task is still the same. So this is up to date. It doesn't have to be executed again. But really what we want is kind of get rid of this kind of programming in the build script. We want to move it to someplace else so the build script can stay declarative. And then we can reuse the task in other places. Maybe we also want to have a chart checksum task in another project, right? So we should really doing this better. So let's try that. And the first step to make it better is to make it worse. So I'm going to add a class in here. It's called checksum. That's going to be my task. I'm going to inherit from default task. And I'm going to declare an input file, and I'm going to declare a checksum file, which is the output file. Because computing the checksum is not really specific to jar files, so I wouldn't call it archive file in here. What should be the type of these? Well, to make it really idiomatic, we would use the provider API. So we would inject something into the constructor in order to do so. Namely, the objects factory. This is just a class that allows us to create Gradle DSL objects. So usually use that in a plugin. We can now use it also in the build script. And we're just going to use it to create a file property. So basically, a property is something that can be evaluated lazily. It doesn't have to be known at configuration time. Maybe it's computed from something else, and we only need to do it if we run this task, which is why this property provider API exists. And the same holds true for the checksum file, so file property. And then there's annotations, so we can say, okay, this is in task input. Sorry, of course it's a task, so it's an input file. And this is an output file. And then we can just write a method where our implementation should go, annotated with task action. So I'm just going to call it generate checksum. And basically the code we've written in the do first block up here goes in here. We slightly renamed the variables, and this is now also a property, so this should be as file. Yes, so now these properties only get evaluated here if I call get on them. Then whatever is backed in there gets evaluated. Actually, for the checksum file, I don't want to make people specify it necessarily. You could override it maybe, but I really want to use a convention, which I did up here, right? So basically, I'm going to always use the same location as the input file and just append a different extension to it. This is going to be my default. Kind of a default value. So that should do it. And now I've defined this custom task class, but I haven't used it yet. So how do I use it? Instead of registering this generic default task, I can give a type parameter here when I register the task. And then I can basically move most of this. I only need the archive file because I need to set the input file. Right, so if I run this again, the file is still there and it has the same content, but now it's generated by my custom task class, which I've defined inside the build script. So we're still not quite there yet, but I hope you can guess what the next step will be. Moving it to build source. So, oops, wrong. Okay, first, before I do that, I could do it now, but generate lots of compile errors. I need to add the Guava dependency also to build source. It's just a regular project, so I can have dependencies. It's just an implementation dependency. No one should know that I'm using this. No one should have it on their class path just because the implementation uses it. Of course, this doesn't work because the depth class is compiled in the build source project, so I would need a build source project or something like that, which is not really necessary for this one simple dependency. And we don't really have to enforce that it's the same Guava version in build source than in our production code. I mean, it would be nice, ideally, but we don't necessarily have to couple those two things. Okay, now that I've done that, I can import the changes once again, and then I should be able to move that class without too many warnings to the build source project. Yes, this one, okay. And then I can get rid of this whole build script thing, adding Guava to the class path of all build scripts. I don't need that anymore. Okay, doesn't quite compile. IntelliJ has broken the imports. Let's fix that. This is this import, and that's that one. So as you can see, the editor experience is not bad, but it's not quite there yet. So we're, of course, talking to JetBrains to make that better. Okay. So the build runs. IntelliJ hasn't quite picked up that yet. Just re-import that. I don't know why the application should not be there anymore. Doesn't make any sense. Okay, now it works again. IntelliJ was a little confused. So what we've done now is in the build script, we only have these 3 lines that register a task that's called jar checksum. It's of type checksum, and it sets the input file to the output of the jar task. And that's all we need. The dependency on the jar task actually is tracked implicitly. So if we call jar checksum, jar will still get executed because basically this jar property knows that it belongs to the jar task. It's produced by the jar task. So it will add a task dependency automatically for us. We don't have to do that manually. So this is really a nice way to refactor custom logic into build source, so you can use it not only in this one project, but in all other projects. And also you get a cleaner build script if you don't have this kind of chunk of code in there and this extra class path dependency in your build script. Yes, and one thing I actually wanted to show also was you can now write tests for that thing. So let's again stash that. I'm not going to write the test now, it would take a little too long. But we can go here again, and then we can navigate to its test. And yeah, okay. I haven't imported the dependencies yet, so what I did, I added Gradle test kit, which is a library that you can use to test Gradle tasks and Gradle plugins with. And I added JUnit as a dependency here, so I can use that in my test. So this is from test kit. A Gradle runner is just a wrapper around Gradle. And in my test, this is now a Groovy DSL. I declare my checksum task with an input file. I run Gradle, and I can then check, okay, does the output file exist? Does it have the content I expect? Basically, I can test my task, my logic that I have. And this is automatically run when I just run my build. So you just run Gradle build. You can see the first steps here is build source, compile Kotlin, and then also build source, compile the test classes, build source, run the tests, and so on. So that's automatically done for us. We don't have to care to make any special configuration for that. So if you have some complex logic, you should also test it. It's part of your build. You depend on it every day. So that's why you can write tests for it in build source. All right. Last but not least, I'll show some custom configuration things that you can do in the build script and that you might want to separate into a separate build script. So since I only have 5 minutes left, I'm going to take a little shortcut here. All right, so I'm going to show that to you in that way. Okay, let's see. So in my CLI project, what I've done here is I've added a bunch of stuff. So this, for example, what I want to do is I want to add a source set for my integration tests. So if you look at the project structure now, we have source mains and source tests, and we also have source integration test. And if I import that in IntelliJ again, didn't quite auto-detect that change. We also have the same kind of support for it. We can edit it like a normal Java class. We can run it, everything. What this automatically does for me is create dependency configurations for me, like integration test implementation and integration test runtime only. And I've set it up here in a way so that my integration tests can see all the classes from our main source set, which is what this does. And also the runtime class path is adjusted in the same way. And also my integration test implementation dependency configuration can see everything that's on my test implementation, my regular test implementation configuration. And the same for runtime. So what does this give me? I can now also add dependencies that would just be visible for the integration tests. So in this example, I'm using Bartholdi, which is from Christian Stein, who's also here today. I'm going to give a talk later about testing in the modular world, which is basically a simple wrapper around some executables. So what I'm doing here in the integration test is I'm running Java on my main class. So basically I'm passing the app class name and the class path of the main class here. And in order to do that, to execute that test actually, I'm also registering a new task, an integration test task, right? So this is in addition to the regular test task, it would just execute the integration tests. So I can call those separately. And since I want to give it the main class path, but I don't want to download dependencies when when Gradle just reads the build script, I'm using this command line argument provider down here to delay that, basically resolving that file collection, which is actually just the runtime class path of my main source set. So this all works and it's fine, but I have this chunk of stuff here, right? It's kind of a lot, and it's kind of has the same focus, the same concern it solves. Also have this piece I haven't explained yet. So there's a check task, which is kind of like a lifecycle task that depends on the test task by default. And I also adjusted that to depend on integration test. So whenever I call Gradle build, it will depend on check, and check will depend on test and integration test. What I want to do is I want to refactor that. And let me just show you the end result. It's really just, this is a simple refactoring really compared to the other ones. So what I've done here is I've created a new plugin called integration test. And all I had to do for that was take these pieces of code that we've seen, creating the source set, adjusting the configurations, adding the extra test task, wiring it to the check task. I've done all that, and it's now in the integration test plugin. And where does that come from? Well, it's in build source again. In source main Kotlin, there's an integration test Gradle KTS file. So it's really similar to the build scripts that we had here. It just has a different name. So it's called integration test, which becomes its plugin ID. So it's called a precompiled script plugin. So it's kind of like, in the old days, you could also do that. You can like take chunks out of your build script and put them into a separate build script and include that build script basically. But this is a different thing, because this gets compiled only once, and then you can use the binary of it, which is why it's called a precompiled script plugin. Yes, so basically all the things that we've seen previously are now in here, and I don't need to worry about them in my main build script. I'm just going to say, okay, in this project, I want to use a separate integration test source set, and my convention for doing that is just, okay, let's apply the integration test plugin. Right? So this is a simple way to group things that belong together in one build script and apply it in different sub-projects, for example. The next step that you could do is now also to extract this out of your project, out of build source, into a top-level project, so you can reuse it in different independent projects. That's basically just one step more. Just set up a top-level project, put it in there in source main Kotlin. That's it. Yeah. So this is kind of a step-by-step refactoring strategy that you can apply, and you can see how often is this used. Do I want to extract that maybe? All right. So in summary, you should really strive to keep your build scripts declarative and use build source as a simple way to share build logic between sub-projects, to collect common dependency versions, for example, and so forth. That's like the bottom line of this whole quick and dirty to safe and sound talk today. There's 2 links here. I've put the demo code on GitHub, and the talk is already, it will be linked, not already, on there, the slides and everything. And there's also my other talks. So if you're interested on JUnit or anything, you can take a look there. There are some recordings up there. And with that, thanks for your attention.